Hi, this is an AP chemistry video. We are going to cover parts of 8.1 to 8.6. Not quite sure how far I'm going to get, but so we are going to start talking about chemical bonds. Chemical bond is a force that's holding groups of atoms together. Then they kind of act as one unit, and the something called binding energy would be the energy that would be required if you were going to go and then break that chemical bond. So this is kind of showing you that the this is kind of showing you two hydrogen atoms at the top. They can be kind of far apart and not really have any interaction at all. Then they can start to interact, and finally they will reach this optimal distance where the electrons that are in the bond are being attracted to the nuclei of the opposite atom. We're going to also just talk about ionic bonding. The previous was the covalent bond between nonmetals. Ionic bonds are electrostatic between cations and anions, and they result in a crystal lattice. So they are usually between a metal and a nonmetal, or there can be polyatomic cations and anions that are involved also. Coulomb's law, we can use this for a lot of different things. And on our, this isn't technically Coulomb's law, but it's very related to it. Coulomb's law is that force on your formula sheet. Force is directly proportional to the charge of one particle times the charge of the other over the radius squared. So what it's showing you is that the smaller the distance between two charged particles, the larger the force of attraction. And the greater the charge of those particles, the greater the force of attraction. Or repulsion. If they're like charges, they would be repelled. But normally we're talking about it in terms of attraction. So we can actually calculate the amount of energy between a sodium ion and a chloride ion, because we know the distance between the ions is about 0.276 nanometers. So here is your Q1 and your Q2. So this one doesn't have the radius squared, but it's still proportional to the distance between the ions. So this is an example of a potential energy curve for a covalent bond. Right here, first of all, let's look at kind of what the axes are showing us. So their intermolecular distance in picometers is what's on the x-axis, and then potential energy is on the y. Notice it's 0 here, and then it becomes negative or it becomes positive. So the first thing we would have is if the two hydrogen atoms are far enough apart, there's no attraction or repulsion. So the potential energy would be 0. The next, as they start to get closer together, now there is some attraction and not much repulsion. So the potential energy now is starting to slope down. And then we do get to, and it kind of cut off, this ideal distance. So these are the hydrogen atoms bonded together. And this would be the corresponding to the lowest amount of energy, which means it's most stable at this distance apart. It balances the attractions and the repulsions, because the electrons are going to repel one another from one atom to another, but this is a good balance when it gets to this ideal distance. So the distance here would be the length between the cation and, or no, this time it's not a cation anion, it's covalent, so it would just be the distance between the two hydrogen atoms when there is the bond is formed. So this energy would be equal to the bond energy, the energy that would be required to break the bond. It would be positive because you'd have to put energy in. It would be endothermic, but it is that value. And then here's another kind of showing you more clearly without everything being cut off, that ideal bond length. So the distance, you can read that from the x-axis. And then lastly, if you continue, putting them even closer together, you get to a point where they're unstable, that the repulsions between the atoms are too strong, so potential energy increases. So this is the one that's in your textbook. It's very similar. I mean, it's the same diagram, just explained in your textbook. So when we're talking about that previous example was a covalent bond, electrons are being shared by the nuclei mutually. So these electrons are attracted to both nuclei. Remember electronegativity. Think about, well, what is it and what was the trend? So electronegativity is the ability to attract electrons that are in a bond to an atom within a molecule. And the trend is, in general, it gets bigger as we go to the right towards fluorine, which has the highest electronegativity of the elements at a 4.0. So the key words here are that it's the ability to attract shared electrons. So those are bonded electrons to itself. These are the general differences that we use for deciding whether or not something is covalent or ionic. These are different depending on who you talk to. So they're not necessarily always going to be true. Because it's not just a definite all of a sudden, oh, it changes to ionic. All bonds have some ionic character unless they are just two identical atoms in a bond, like a diatomic molecule. But in general, if the two atoms have a small electronegativity difference, they're sharing their electrons equally, somewhat equally. And then when it gets bigger, what we get, still they're sharing, but we call that a polar covalent bond. And then it gets to the point where we would say, though, now the electrons are being transferred from the metal to the non-metal, and that's what an ionic bond is. So all bonds have ionic character. We'll talk about that more later. But let's do a couple of questions here. Now we're looking at, which of the bonds is going to be the least polar here. So what we're looking at, and we're going to try not to use any electronegativity values because we don't really need them. We can just use the trend in the periodic table. So for letter A, notice they all have fluorine. What is changing is, the other elements. So we've got a nitrogen, an oxygen, and then we have a carbon. So the greatest difference in electronegativity is going to occur between the carbon and the fluorine. So that is going to be the most polar of the bonds. So we would rank, we would write CF has more polarity without even looking up those electronegativities. The next would be the nitrogen with the fluorine. So this would be the most polar. And then we would have the nitrogen and the fluorine. And then the least polar would be the ones that are closest to each other in electronegativity. So there isn't that great of a difference. So there isn't a big disparity between their electronegativities. And that would be the O and the F. So you could pause the video and try the next couple. For these now, we are going to kind of look at separate combinations. So first, carbon and fluorine. That's going to be very polar. And then we can look at silicon and fluorine is going to be even more polar because there's even, as we go down a group, electronegativity decreases. So there's going to be an even bigger difference in electronegativity between those. And then the nitrogen and the oxygen are going to be very close in electronegativity, so not as polar of a bond. So if I were ranking these, the most polar is the greatest difference in electronegativity. To the least polar would be the one with the smallest difference in electronegativity. Again, not using my periodic table, just looking at the trend. Next one, so these ones are all bonded to chlorine. And we can say our least polar for sure will be this diatomic. That's the only truly nonpolar molecule. And then between, if you think about the boron here versus the sulfur, there's going to be a greater difference in electronegativity between the boron and the chlorine. So that'll be the most polar, and then the sulfur and the chlorine, and then the chlorine. So we'll do a couple more. When you see the question, you definitely could pause and see how you do. This one's a little different. This one which of the following are the least polar, but they're still polar covalent, so they're not ionic. So right away you can eliminate this one because it's ionic, and you can eliminate this one because that one's truly nonpolar covalent. I know the first one's ionic because it's a metal and a nonmetal. So now I need to rank kind of and pick the one that's, these three are all polar. They all have oxygen, but which one will be the least polar? So again, I'm just going with the trend in the periodic table. Nitrogen and oxygen. I'm going to look at silicon and oxygen and carbon and oxygen. So for this one, the least polar is going to be this one because these two are closest in electronegativity. Similar question number 3 is now which one would be the most polar? So again, we can use that same reasoning. We know it's not this one because it's ionic, not this one because it's diatomic, so it's nonpolar covalent. So now we're going to pick this one because silicon and oxygen are going to have a greater electronegativity difference than carbon and oxygen or nitrogen and oxygen.